Yeah, thank you. My name is Marius Hoggenmueller from the University of Munich.
And I'm Martin Tomitsch from the Design Lab at the University of Sydney.
And we present our work on the design of low-resolution lighting displays, which we did together with our colleague Alexander Wiethoff. We live in a high-resolution world. Here are two examples in the context of the smart home, where more and more data is collected through the Internet of Things, and often this information is represented through high-resolution screens. And while there's certainly a place for such high-resolution screens, we question in our work if such interfaces are designed to represent data in an intuitive way, or maybe rather for an expert kind of user. And further, we question if such products are not just another gateway for placing more advertisement in our private sphere. So in our work, we explored an alternative type of displays, so-called low-resolution lighting displays. And through recent developments in LED technology, the creation of new displays were enabled, and this kind of displays are more seamlessly integrated into digital products, and they can visualize information in an ambient manner. In the past, also visual artists have repeatedly used low-resolution lighting displays as a creative material in their work, and here you can see two examples from Jim Campbell, and he demonstrates well that information can be also conveyed in a very low resolution. Campbell also experiments a lot with different kind of materials, and here he shows that working with light always means designing lighting as a material. So over the past 4 years, our two research labs have conducted several experimental design studies which involve the design and deployment of such low-res display applications. Here you can see low-res urban furniture, where we explored gamification elements in cities. We also used low-res media facade to prototype novel interaction techniques together with citizens. We had a look into public transport information and how such information can be visualized through low and high-res display technologies, thereby finding the sweet spot between aesthetics and functionality. We then also integrated low-res displays into a prototype of a future bus station. And finally, we also had a look into non-lighting low-res displays. That's a so-called flip dot display with a mechanical system to either show a black or a white dot, and we used it to visualize real-time information about domestic electricity usage.
So based on our own work over the past 4 years and also a review of related work in this area, we identify in the paper 5 challenges for designing low-resolution lighting displays, which we categorize into artifact challenges and process challenges. And so the first artifact challenge here is designing low-resolution content and interfaces, which relates to the fact that when we are designing such displays, we're dealing with very unusual dimensions, sizes, ratios, resolutions, and even form factors in some cases, which is very different to when we are designing for more traditional computing display applications. The second challenge here relates to encoding information in a low resolution, which is something that we found in our own work, but has also been identified in previous work, such as, for example, in point lights, which was presented at CHI in 2012, and in the context of low-resolution media facades in a paper presented at a Media Architecture Biennale in 2014, where the authors are suggesting to use, for example, flashing lights and flashing light patterns to encode information, or, as in the case of media facades, to use color, movement text, images, and even the architecture itself to encode information and communicate information to people. The third artifact challenge relates to designing the screen as a material, which we found to be an incredibly important aspect of the design process in our own design cases. Because when we're designing low resolution lighting displays, we can choose from a vast range of potential lighting materials that all have different form factors, affordances, and therefore also result in different experiences. So it therefore becomes very important, but it's also a challenge to design the screen as a material. And again, we can also see that being explored in previous work, such as Jim Campbell's media art work on material light that Marius already introduced earlier, but also through a paper presented here at CHI last year, where the authors explored the use of 3D printed optics to design the aesthetics of illuminated objects. This brings us to the process challenges, with the first challenge here that we identified being the involvement of stakeholders as co-designers. And while there is a lot of work available in HCI that has dealt with identifying methods and approaches, ways of including stakeholders in co-design processes, we found this to be a specific challenge when we're designing low resolution lighting displays because of a lack of resources to communicate both the opportunities but also the constraints of such displays. And linked to that, we also found it an issue that there were no out of the readily available tools that we could use in those co-design sessions to allow our participants to design what the envisioned solution might look like. Which is linked to the next challenge, the final challenge, which relates to a lack of flexible tools to support design exploration and iterative refinement. And again, while there are a lot of tools and toolkits available that support the design of other HCI systems, we found that at the time there was no tool available that specifically supported the design of the iterative design of low resolution lighting displays and allowing for exploring different types of fidelities and doing that in a way without having to have the necessary technical skills and electronic skills to prototype such systems. And so to better understand these challenges and also to identify how we can address these challenges through a design process and through design solutions, we went through a design research project that involved the design of a new lighting display.
So to frame our research into a real-world case, we collaborated with a Sydney-based startup, Solar Analytics, and their product is a web-based monitoring dashboard that shows solar panel owners information about their current solar production and also about their energy consumption. And at the beginning, Solar Analytics told us that most of their customers are not regularly checking the information on the online dashboard or on their smartphones. And Solar Analytics was therefore really interested to launch an in-home low-resolution lighting display to have the information more physically embedded. And they also mentioned that they do not have the expertise to prototype and develop such a low-res lighting display by themselves, and so they were a really good target audience for our research project. So during this user-centered design process, we developed a toolkit that allows to sketch low-resolution visualizations on a paper prototyping level, and using various translucent materials such as watercolor paint, water-based ink. And we then created different physical overlays that you can use to simulate different pixel patterns and lighting qualities. And finally, there's an iPad used as a backlight source, but also to augment the physical display mock-up with dynamic lighting patterns. And we also presented this work last year at TAI, so if you want to need more information about the technical aspects. So we applied this toolkit during an initial design workshop that we held with the product team of Solar Analytics, but also with their customers. Because of the limited time, I want to introduce now already the high fidelity prototype that we designed based on the insights from the design workshops. So we designed a novel type of low resolution lighting display that features a discrete and a continuous display mode. And therefore we were using a stepper motor that moves the LEDs back and forth. And this allowed us to support a wider range of visual representations. So in the discrete mode, we were able to show text, and in the more continuous mode, we could show ambient and analog images. We then created 5 distinct visualizations for this display based on the findings from the design workshop. And 2 were designed for the discrete pixel mode and 3 for the continuous mode. And there was one purely text-based visualizations, and the other ones were using visual encoding such as color, area, or brightness. And 3 of the visualizations represent live data, whereas 2 of them represent past energy performance data. The particle visualization number 5 is distinct from the others in the regard that it's using speed and movement as an information encoding, which then also results in a constantly moving image. So we were trying to keep the interaction with the display quite simple. So we only attached a physical knob for controlling the brightness, and we designed a web interface for more sophisticated kind of options. For example, the interface allowed to change the colors of the visualization, which was one proposal from one of the customers. She said that she wanted to adapt the visualizations to her interior design in her living room. We then deployed the final display prototype in 3 different family households in Sydney, and all of them were using the Solar Analytics dashboard before, and also all of them took part in our initial design workshop. We then also collected several data for evaluation purpose. So we collected log files and conducted interviews after the deployment. And more findings regarding the usage behavior with the display can be also found in an upcoming publication at this year's PERDIS in Munich.
So based on our design case studies that Marius introduced at the beginning of the talk, and our review of previous literature in this area, and an analysis of the findings from our design research study, we identified in the paper 10 design recommendations for designing low-resolution lighting displays. In the remainder of this talk, we will focus on 5 of those design recommendations, which we have categorized into recommendations relating to the aesthetics of low-resolution displays and relating to the interpretation of meaning. The first design recommendation is to use spherical lighting compositions, which was something that we found participants to explicitly refer to as being perceived as aesthetically more pleasing in the study. And interestingly, they referred spherical or also circular visualizations over rectangular visualizations, despite the fact that the display itself was rectangular. This was also linked to movement, and so movement seemed to additionally increase the aesthetic perception of the visualizations, as is illustrated in this short video excerpt from the interviews.
The particle one, if I wasn't consuming any energy, like at night, and the particles weren't really moving, it wasn't attractive.
Basically, I would have it so if we're at our peak, there should be so many particles there. It's like insane amount of particles, and I'd have them maybe going in different random directions, not all just into the centre.
Okay.
So it was much more artistic.
The second design recommendation in this category is to utilize the whole display space, which is again different to when we're designing traditional information screens or for traditional displays, like even for a projector, for example, where if you don't use the screen for information, it's just black. But interestingly, our participants also specifically commented on the fact that those of our visualizations that did not utilize the entire display space were perceived to not be as pleasing, as aesthetically pleasing as the others. So our recommendation, therefore, is to always activate all of the LEDs in a display. And again, this is also linked to the fact that we are designing these screens in a way as a material and the material experience. And that's very different when we're working with LEDs and light as a display material compared to working with traditional computing displays. And the third design recommendation is to use randomized visual elements, which again was perceived to be aesthetically more pleasing by participants and to be more interesting visualization and a more interesting way to encode information. And is something that we explored or were able to explore in particular in our particle visualization.
Another section from our design recommendations are related to content and the interpretation of meaning. And here we have another short video. What you liked about the numeric representation?
Just so clear. I mean, it's so clear. Like, you know,
Precise.
it's precise.
Generally, we prefer this one. It gave us up to 3 pieces of information at the same time. And the speed was a really clear indication of, you know, how quickly things were moving and how strong the solar output was.
Please maybe look at the dashboard more.
Yes, so he was looking at that and comparing what he was seeing visually with the numerical.
So as you just heard, some of the participants liked the numeric representation because it's so clear and it allows an immediate understanding of the data. The particle visualization, so the more abstract, was liked because of the more artistic concept, and it allowed the user to foster data exploration. We also found that particle systems are quite suitable for encoding live quantitative data, and this is also tied back to one of the first design recommendation, because with the particle visualization you can use the entire display screen through moving particles across different positions, and also the particle system are quite suitable for randomization effects. So to sum up our talk, we first identified challenges for the design of low-resolution lighting displays based on 5 design cases we did in the past. Then we reported on our approach of using a user-centered design process supported by a toolkit to design a low-resolution lighting displays. And finally, we present design recommendations that hopefully help lighting designers when creating low-resolution lighting displays in different contexts. For example, for products for the Internet of Things, or also for autonomous vehicles. So thanks a lot for your attention, and we are happy to answer any questions.
Well, then I have at least one question to pop you. Someone there. Good.
I do have a question. Can you tell a bit more about, so one of the things you reported is that your participants enjoyed these ambiguous movements. Do they have other suggestions about how the, versus the numeric displays, how the sort of non-representational displays should be designed, or what that design should be like, or were they able to articulate that at all, or was that really kind of left to you? For example, you were saying that particle systems really lend themselves to randomization effects. Well, there's a lot of different ways you can do the randomization. Did you have a chance to explore with them what that might look like at all?
So thank you for your question. So, for example, one thing the participants said was that you could also use randomization with colors. So, for example, that you have a specific spectrum of colors and have some randomization effects in this regard. Yeah.
And I think it's also, just to add to that, it's also always a little bit of both. So in our previous design cases that we've done over the past 4 years, where we often weren't able to do co-design sessions or as in-depth evaluations, we often found that it's always a process of doing a lot of experimentation. And while that's commonplace with any HCI development, that we do iteration, we found this to be sort of quite different when we're designing lower resolution displays, in that there's a lot more experimentation with the material, because it's something that is to a lesser extent explored so far.
And I'm not familiar with the previous work, but have you released the co-design toolkit as a resource that people can use? Or have you thought of it?
Yeah, the toolkit is online, so the iOS application is on GitHub, and we also have the for the display configurations, the laser cut files, and yeah.
Thank you.
Hi, my name is Pratik Shah from HP. This is great work. Thank you for sharing this. My question was, so do similar design principles also apply for representing lighting states on user interaction? Like if I take an active step to interact with the device and it presents some kind of lighting state to me, do these design principles still apply to those states?
Whether the recommendations that we identified apply to that, or whether
Yes.
principles in general? All right.
Right.
Okay. So our recommendations were more specific to the design of content, designing content and encoding information in low resolution lighting displays. In these recommendations, we didn't explore interactions as much. So that was the focus of this particular paper, looking at aesthetics. We have looked at interactions in some of the various design cases, but that probably would be different recommendations that could be explored in some future work, potentially.
Okay, thank you.
Did you want to add anything there?
That's fine.
No.
Thank you, and by this we conclude this session, and thank you for contributing with your questions to turn this into a lively session. Thank you.